So this week in lab, we're actually going to combo two labs, the EKG and Microcirculation lab. The EKG lab is a little difficult because it's not like you're in front of the computer, but we do have a way around it. With microcirculation, it's very hard to use a microscope to look at a fish tail at home when you don't have a fish, the chemicals, or the microscope. So we're going to do two different labs and put them together. This way, your current final exam week, you would not have a lab. So you should expect the quiz for the next 2 weeks will follow the objectives for these next two labs. So here's the objectives for the EKG lab. You're going to need to know objective 1, 3, 4, be able to define these. And then when we look at the placement for the 3 standard limb leads, those are in the packet. So, for lead 1, lead 2, and lead 3, you're just going to have to know the placement, like right wrist, left ankle. So just know where the 2 locations for each one of these leads are located, and you should be just fine. As we move into your textbook, one of the pathways that you need to know is how the action potential travels through the heart and where it initiates. So if you look in your lab manual, I'm actually in exercise 31 on page 450. So when we look at the action potential through the heart, it initiates in one of 2 pacemaker locations. At the top of the right atrium is the sinoatrial node. The bottom of the right atrium is your atrioventricular node. When we look at the SA node, it runs about twice as fast as the AV node, so your sinoatrial node will be the lead pacemaker of the heart. So the action potential initiates from this SA node, and you're going to see it spreads across both atrium. As it goes across the atrium, it will initiate contraction, and then as it hits the bottom of the right atrium, you'll see it hits the AV node, but at the AV node, the impulse is paused. So what does that mean? Well, when we look at cardiac muscle, the intercalated disc, in theory, should send the action potential straight down through the heart. However, we know that the fibrous skeleton, the trigons, whatever term you want to call it, is going to electrically insulate the atrium from the ventricle. And the reason we need to do this is because we have got to, squeeze the atriums. They have to go through that period of systole and then wait for blood to flow. So that impulse is paused just for the briefest of periods to allow for the blood to finish emptying from the atrium to the ventricle. Now, the pause is not very long, 0.1 seconds. But if we look at a cardiac cycle of 75 beats per minute, the cardiac cycle is going to be 0.8 seconds. So 0.1 of 0.8 really is actually a significant amount of time. From there, it's going to go down what's called the AV bundle, but it's also referred to as the bundle of His. It's spelled His, but pronounced His. You can see partway down the AV bundle, it splits into right and left bundle branches, and those bundle branches travel down the interventricular septum in the middle of the ventricle. Here at the apex of the heart, it's going to go up what are called Purkinje fibers. Now, these fibers are very, very fast, and the reason why we want those Purkinje fibers to be so fast is because the ventricle has already started contracting. We do not want the ventricle to contract and then the outer walls to contract. We want it to be one nice smooth contraction. So we send it up these really, really fast fibers. You probably have recognized that term. We talked about Purkinje, very, very fast Purkinje fibers when we looked at the cerebellum in 205. So that term is probably something you're familiar with. One of the objectives that you need to do is to be able to draw an EKG. Now, you're not going to have to draw an EKG per se, but you need to understand the parts of an EKG. So if we draw it, it'll make it easier to learn. So when we draw it, we have a nice straight line. We get a small inflection, a short flat line. We go down, big up, come down again. And then the third peak is bigger than the first, but smaller than the middle one. So this first peak is P. This mark right here is Q. Top is R. This is S. And this is T. When we look, those letters don't actually stand for anything, so you don't have to figure that out. But I will abbreviate a little bit. A is going to equal atrial. V equals ventricular. D equals depolarization. And R equals repolarization. So if we were to ask you, where is this point? If I said, if I would draw and I'd say, hey, what's this point? Make sure you answer just Q. If you answer QRS complex, I'm going to mark it wrong because this location is only Q. So don't be lazy. Make sure you know the exact position of that. So when we look at what each peak represents, this small inflection P, this is going to be atrial depolarization. Within QRS is atrial repolarization, as well as ventricular depolarization. And finally, the T wave is ventricular repolarization. So remember, when we look at depolarization, that'll result in contraction. As we turn the page in your book on page 451, you'll see probably a much better illustration of an electrocardiogram, obviously right here and right here. When you analyze an EKG, things to pay attention to are, do we have even spacing of these waves? And are the peaks relative to where they should be? The P wave by far should be the smallest peak because this is just looking at atrial tissue. And as we learned about heart anatomy, the heart does not have a lot of myocardium in the atrium because its functionality is minimal. Contraction is very minimal in the amount of blood. Remember, most of the blood goes to the ventricle by passive filling. So since there's less myocardium, there will be less electrical activity. When we look at QRS, this is going to have the addition of the ventricular depolarization on top of that atrial repolarization. And then T just looks at the magnitude of ventricular repolarization. R should be very easy to see, very easy to define on any EKG. Another objective for your EKG lab is to define a few words. So over here are some definitions, although we do have to modify the definitions a little bit to make it more complete. So when we look at tachycardia, it's a heart rate over 100 beats per minute. And make sure you add the words at rest. So this is abnormally high heart rate at rest over 100 beats per minute. Yes, you need to know the numbers. The reason why we add at rest is because, to be honest, I could hop on a treadmill and within 30 seconds, my heart rate would be over 100 beats per minute. So this is looking at, is your patient been lying on a gurney for a half hour and they're still at over 100 beats per minute? That tachycardia, that could indicate several things. If you're not looking at cardiovascular events, being tachycardic is an indicator of pain as well. Bradycardia, it's an abnormally low heart rate, and we normally accept below 50 to 60 beats per minute. Now, I have a friend who teaches aerobics and classes at a gym, and her resting heart rate is 47 beats per minute. By the way, she's over 50 at this point. So does this mean she's bradycardic? Well, that's where the term abnormally low comes in. Because she's in sick good shape, her heart muscle, her myocardium has increased in strength, and when her heart contracts, it will pump more blood. So I need to pump 1.5 times the rate that hers does because my heart is not as strong, as fit. So people who have really good heart rates that are below that 50 to 60 beats per minute, they tend to know their heart rate. They track it because they are people who tend to be in shape. So if you're doing a pulse and somebody has a heart rate below that 50 to 60 beats per minute level, don't ask them if that's normal, because if I'm having a nurse assess me and somebody asks me if something's normal, that's going to freak me out and you're going to send me tachycardic. So just the first question you should ask is, do you exercise regularly? If they exercise regularly, then they probably know their heart rate is normally low. We look at fibrillation. This is uncoordinated heart contractions. If we didn't have coordination by our pacemaker cells and our blockage of the action potential from atrium to ventricle, we would have maybe the atrium and the ventricle trying to contract at the same time. And I think at this point you understand why that wouldn't work. As we turn the page in your lab manual to 452, what you have to understand is that EKG only shows electrical events at the heart, of the heart at the level of skin. This does not show contraction or relaxation whatsoever. However, to have a good visual, this is showing you what should be occurring during these events right here. So for those of you who need a visual illustration of what's going on, this on page 452 is really, really helpful. Now, as we continue through this page, you can see we've got what's known as Einthoven's triangle. This is looking at where do we put limb leads. I was really sick a few years ago and I woke up with horrible, horrible chest pain. Went to the emergency room, said I had massive chest pain. That woke me up. And before they even knew my name, they had me in a room and were collecting electrocardiogram. How they did that is they put they ran what's called 12 leads, where they put electrodes at various parts of my body to monitor different aspects of the heart. So when we look at what happens, these are called limb leads. These are electrodes at very, very certain positions. So you are required to know where the limb leads are for the first 3 leads. So when we look at lead 1, it's going to be on the right arm and left arm. So if you're, I have students who do like this YMCA thing. So we're going to have right arm and left arm for where lead 1 would record. And when we look at this, this is what recording across what's known as the base of the heart. So it makes sense that if both arms would be the atrial electrical activity. Lead 2 is going to be the right arm and left leg. So this is going to be looking, and this is what the standard EKG we drew. It says what's going from top to bottom of the heart, and that makes sense where that's located. If we look at lead 3, this is going to be the left arm and the left leg. So when we look at this obviously looks at just the left side of the heart. Why do we care about that? Because the left side of the heart is what's pumping out to the body. And if we don't get blood, oxygen, and nutrients out to our 75 trillion cells, we don't collect that CO2 waste product, we're in a world of hurt. The right side going to the pulmonary circuit is important, but if we're not delivering the nutrients to our cells, we're in big trouble. So make sure you know where those 3 limb leads are located. If you look in your packet, it explains that pretty quickly as well. So how do you do this week's lab? I'm showing you this week because there's some special differences that you need to be familiar with. So we've got the lab videos. They're really good videos. Obviously you found this one here. Dr. Griffiths has 4 videos explaining the microcirculation of the heart, so I'll talk about that in a minute. But when we do the data sheet, you're actually going to start here, and then you need to go to LabScribe and download the LabScribe software from this location. Now, each iPad or computer I've tried to use opens up another Blackboard window with another link, so you'd have to click that link and download the zip drive. You don't need a password, but you might have to click a second time, so it may pop up a new window. You're going to download the zip drive, extract it to your computer desktop. We've got Mac, Windows, and then these sample data files. You can ignore those sample data files for now. We'll need them a little bit later, maybe. So whatever is appropriate. I have a Windows-based computer, so I opened that one. And then this says, hey, follow these few steps right here. You're kind of used to clicking OK when you open up LabScribe. Now, the data file that you're going to analyze is this one right here. And when you look at the data file, you need to pay particular attention to what you're analyzing. So you're going to see that cardiac cycles are marked by the first letter of your last name. So when we look at, U through Z, that's what I'm going to use because my last name is Vietti, the first letter is V, so I'm going to analyze the cardiac cycle at that mark. So the first letter of your last name, that's the mark you want to go to analyze. The data sheet is right here. We'll take a look at it in just a second. Do not delete this right away. We're going to be using this for one more lab this semester. So when you open up the file, it will look something like this. It may look a little different because this is a stock photo, but 3 windows will pop up. You can see here's the actual EKG. This shows you the pulse and then the pulse integral. I normally ignored this channel. Quite frankly, it's in the way. So you grab the arrow to shrink this down, and then these 2 can get bigger, okay? Because we only need these 2. So in the lab, you would have been hooked up to the iWorks machine. It would have collected an EKG, and then you would have that pulse plethysmograph on your finger to collect your pulse. What we did in 205 when we were first learning the tutorial. So this represents the electrical events that are occurring, and this is the physical manifestation. The pulse plethysmograph would have been on the finger, while the EKG would have been collected at the wrist. So you can see there's a slight delay from when the electrical event arrives to that physical event of the blood going through. Illustration here. Let me clean up some of this out of the way so you can see what I'm doing. So the R pulse interval would be to have one cursor here at the R and the other cursor here at the peak of the pulse. So you're going to measure the time difference between when the electrical event arrives and the physical event. And if you would look just at the EKG file, when you do the analysis, this is what it should look like. You should have, you're going to have the other channel, the pulse, open too, but I don't have just a picture of that. But you need to remember you're going to put a cursor here and a cursor here, and then you hit zoom between the cursors, and that will get you here. Don't forget to auto scale, and that will help you do the analysis. Then if we look at the data sheet, jump to that illustration, you're going to put a cursor here at the R, another cursor here at the R, and then up here it would say T2 minus T1 equals blah, blah, blah milliseconds. Okay, so maybe 800 milliseconds. So this is R to R. Remember, this is time 1, time 2. So this horizontal axis is monitoring this time. So at that point, you would go to your data sheet. We actually need the other. Because when I measure this a first time, I measured the distance from the time from here to here. Well, now what you're going to be doing is what is the length of each part. So to measure P, I'm going to put a cursor here, and I'm going to put a cursor here. That's the P wave. And then what I will do is measure P to Q. So measure P to Q. If you do not flip-flop, unfortunately what happens is you're like, okay, where did I put that? And now let's measure, QRS, and then go measure T, wherever we're going to put T. And then you have to go back and figure out, where did I put this first cursor? Was it here? Was it there? Was it there? And the accuracy dives, because when we look at this data sheet, by the time we're done with each other. So when we look at what you should do, it makes a lot easier is if I put, here's my P, then when I'm ready to do P to Q, all I have to do is move the first cursor, okay? Then you do QRS, and I'm going to move this cursor over here, and then S to T, I move the first cursor, and then T to P. So just flip-flop back and forth, and you're only moving that first cursor. Now, if you look in your packet to the very back, we have this nice illustration that shows you where do I put the marks for this. So that's really helpful guide for you as you're working on this quick. If you look at the data sheet, it's going to say, figure out the cardiac cycle R to R, read the T2 minus T1 box. So if we go back to our, and you would write it in seconds. So if it's 800 milliseconds, it means it's 0.8 seconds. To calculate beats per minute, it's 60 divided by T2 minus T1, and that has to be in seconds, not milliseconds, and that would equal 75 beats per minute. The next thing, the R pulse interval, if we look at that 0.235 seconds. So it seems pretty straightforward. Once you get to that right cardiac cycle and you get 2 cardiac cycles up, this is pretty much what you're going to follow. However, I'm going to give you a word of warning. I normally show this in class, is do the P wave first, then P to Q, QRS, S to T, T, and then T to P. You're going to flip-flop between these, and let me show you why. This number here should equal this number here. So this is the whole, and then these are the individual parts that we will be adding up. And they need to be within 0.1 seconds data sheet. Make sure that you put, which tracing section am I doing? I would put U to Z, and Kim Vietti, and we'll say I'm in the Tuesday lab. This will be really important because now when you guys submit everything through Blackboard, it doesn't always accurately sort you sometimes. So if you put the day, that will help us out too. So that shows you the EKG part of it. Now we need to look at the other half of lab, which is this part right there. So you'll notice the data sheet is different than what's in your packet because we're also adding the microcirculation lab. On this data sheet, you guys are going to look that up. You're going to look in your packet. You can look it up online, but spend some time researching this. So as we look at the microcirculation lab, really focus on this aspect right here. Okay, you are going to have some diagram, and all those vessels are up for grabs. So make sure you're familiar with those vessels. The cool thing is, if you know the subclavian artery, the subclavian vein will be right there. Axillary, axillary, brachial, brachial, radial, radial, ulnar, ulnar. So when we look at these vessels, they're all not brand new vessels that you have to learn. They're located right by each other. As you continue through your studies, you'll find that arteries and veins run with each other. As we look at this list, there are a few things I want to point out to you. When we look at, for example, carotids and jugulars that serve the brain, take blood to the brain and away, you have to be specific. Is it internal or external? Is it right or left? Common, internal, external, superior, inferior. Make sure you have those details, because if you don't have it, then it's marked wrong, because they have different functionality. The circle of Willis is another one I want to point out to you, because when we look at the circle of Willis, these are awesome vessels. You'll see the anterior and posterior cerebral. Oops, I just covered that. Anterior and posterior cerebral and anterior and posterior communicating arteries. These form what's called the circle of Willis. The special circulations you should go through, although Dr. Griffiths made some very nice videos. The role of chemicals on the goldfish table, if you look at the vessels, they're all going to have one of three layers. The internal layer is called the tunica intima. This is simple squamous epithelium. The media is the middle layer. It's the muscle layer. And then the external you're going to find only on the large vessels to help brace them in place. At this picture right here, you can see where that circle of Willis is located. When we look at the functionality of circle of Willis, it's that shunt that will send blood from one side of the body to the other. That will allow for, if you have a stroke, we would try to feed blood from one side to the other. So that's an important set of vessels. When you look at what you have to do for lab, make sure you know those vessels, know the EKG. You're going to analyze that file that we gave to, go to the spot that has your name on it. If you have any questions, email your lab instructor. But I hope you're having a good week. Remember, the lab quiz over the material for last week is due Thursday night by 11:59, and then the data sheet is due no later than Sunday at 11:59. Take care.